All right, good evening, everyone. My name is Robin Fox. I'm with the National Weather Service in Spokane, and we are here for spotter training. And this is an advanced session. So we're going to cover a little bit more than what we did with basic classes. So I hope you'll get to learn some little nuggets of information this evening. We're going to go through some images of thunderstorms and maybe some radar details and try to answer all your questions at the end. So I'm going to go through the slide deck and talk about a lot of the spotter training high points that we need to go through. But at the end, I'm going to open it up for a Q&A session. So if you have any questions, save it for that. You're also welcome to enter it into the question bar as well. So one thing I want to point out is this is GoToWebinar. And if you haven't done it before, there are some sections that you can see on the little tab that talks about where you can add the questions, and I've received some already this evening. And also I have a handout available that you are welcome to download. That is the spotter guide that we use for the, sorry about this. I wasn't able to advance my slide. Okay. Okay, so here, this is a live virtual class, and as we saw, sometimes we can have a little glitch here and there, but hopefully you are hooked up to the internet, you're able to hear me. As I pointed out, there is a little bar on the side that allows you to put in some questions, put in some chats. I also have a handout that is available that you can download as well. So and at the end, we'll save some time for answering the questions. So all of you are in mute mode. At the end, I will unmute you and we can start our question session. So what makes this one different than other weather spotter classes? Well, we're going to concentrate on thunderstorms this evening. And we're going to look at the different parts of the thunderstorms, but then also cover safety, because that is a big portion as well. If you're going to be giving us reports on thunderstorms, it's important to know the structure, where to be when you're observing thunderstorms, and also how to be safe. So we have lots of material we are going to cover. But first, let's go back and look at what's happened over the last couple years with some of our thunderstorm events. So let's remember back in June of 2021, on the 15th, we had a round of thunderstorms that morning. And this is a map that shows the number of lightning strikes that we had that morning. It totaled over 1,200 lightning strikes. So lots of activity that happened and went across the Columbia Basin, across the Spokane area, the Palouse, and especially in Northeast Washington and the Idaho Panhandle. But also with these, we call them nocturnal thunderstorms because they happen during the night, we were getting reports of hail. So here is some hail that was reported by a spotter, terrific, using the ruler and a quarter, showing us how big the hail was 9 west of Pomeroy. And here's a report from Big Creek, Idaho, also showing the size of the hail. So we had some severe storms that morning. Here, Lancaster, Washington, again, using the ruler to show how big it was. So over an inch of hail. And also in Endicott, Washington, another good example of showing the hail with that. So not only lightning, but we did have some severe storms with that. Now, if we look back in 2020, we had an exciting event in June 24th, where we also had some hail. Also looks like it's more than an inch across, so severe hail with that in Naples and Port Hill, also with some tree damage as well. So those are two big reports that we need for severe thunderstorms. So good job from our weather spotters there. And then back on May 30th of 2020, here we had a lot of different types of weather going on with hail and heavy rain leading to flooding on roadways in Ritzville, some tree damage. So we had some strong outflow winds, some lightning, also blowing dust from those gusty outflow winds, and some very interesting cloud formation, especially with this mesocyclone that was captured by Dave in Clyde, Washington. So lots of excitement that day. So just a little review of the National Weather Service. Our main mission is to monitor for severe weather and be able to put out the warnings, the watches, to let you know if it's going to be in your neighborhood, and give you time to protect yourself and your family from severe weather. So that could be from tornadoes, severe thunderstorms, that could be from flooding, winter storms, high winds, so all types of weather hazards. And we have offices all across the country. In fact, we have over 120 offices that are local experts for the area. And our part for the Spokane office covers Eastern Washington and North Idaho. And if you're not familiar with the area, here's our boundary right here that goes from the Cascade Crest all the way across to the Montana border, and then from BC down to just shy of the Tri-Cities. So we cover 13 counties in Eastern Washington, 8 counties in Idaho, and we have elevations ranging from over 9,500 feet in the Northern Cascades to 170 feet along the mid-Columbia River. So quite an array of conditions and elevations. So as I mentioned, the National Weather Service, the main goal is monitoring severe weather, but we have lots of other roles we do as well, which also includes the weather forecasts and issuing the forecasts that go out at least 7 days across our region. We are the behind the scenes people. So we are monitoring the weather and keeping tracks of it, but also working with our partners. That includes the media, and also the counties, the emergency managers as well, to get the word out on severe and hazardous weather. So we also do a lot of preparedness and education, which is a big part of what we're doing this evening right now. So let's talk about some of the tools we have, we're able to use at our office. And one of the big ones for severe weather is our weather radar. It's a Doppler weather radar. And if you've been to our office, which is on the West Plains, you've seen it. It's right next to our weather office. It is the only radar in the inland Northwest, and every weather service office has at least one of them. So the span covers ideally about from 80 miles to up to 150 miles. And we cover a big chunk of our area. Also, the radar has angles to it. So it allows us to take different slices of the atmosphere as the dish inside that soccer ball on the stilts, I like to call it. There's a dish in there that's rotating and scanning the skies and sending pulses of that electromagnetic energy that bounces off of the raindrops and the snowflakes and the hailstones, and gives us returns on our screens in the office to let us know where the precipitation is and where the storms are. And these pulses of energy go not only horizontally, but vertically. So it gives a good idea on what type of precipitation we're measuring. So we can pick out where the hail is versus where the rain is. So that is a really good tool that we have. And with that radar beam going up in angles, we're able to take different slices of the storm that allows us to get more of a 3D picture of the storm. Now, the radar is just one of our many tools that we use. It doesn't tell us the whole story. And as we see in this map here, we don't have full coverage in our area. There are some pockets that we don't have the best radar coverage. So we have other tools that we use to help fill in those spots. Another great tool that we use at our office is the Radiosonde, the upper air observation. So Spokane is one of the sites that launches a weather balloon twice a day, every day. And it's a very good tool to let us know what the environment is like. So we know how unstable things are. So we know where the jet stream is, the cloud levels, what the wind speeds are doing above our heads. Because although we have lots of measurements of how to determine what the weather is at the surface, we really need to know what's going on well above our heads to be able to forecast what's going to be happening. As we know, most of the weather, all the weather that takes place in the atmosphere is within the troposphere, and this is the area that we are able to use to measure the atmosphere with the weather balloon. So weather balloons, we launch them twice a day, every day, once early in the morning and once later in the afternoon. And it takes about an hour and a half to hour and 45 minutes to do the entire trip. It rises up about 10,000 feet high, which is roughly about 19 miles high. And once it reaches its peak, that's when the balloon has expanded as much as it can, and it will pop and then descend down to the ground. And with that, our observation is done, and we're able to gather the data from that. So on our website, you are able to view our soundings. This is what the graph is right here on the left. That shows where what the temperatures are doing in the atmosphere, what the moisture, which is the dew point measurement, and also what the winds are doing, which are all good indicators to help determine what the atmosphere is like to support thunderstorms. So we're able to see this at this website, and also on our webpage, you're able to view our soundings daily in real time. All right, another great tool that we use is called the weather satellite. Right now we use GOES-17. It's a geostationary satellite, which means this camera that is orbiting the Earth from space is parked over a part of the Pacific Ocean and is in orbit with the Earth, so it stays in the same place. And it's able to take the images of the clouds and the storms and give us some really detailed pictures, showing us, we're getting data from GOES-17 every 5 minutes or less, which gives us a good idea how the clouds are developing. We can see fog developing in some of the river valleys. We're able to see clouds, the tops of the storms developing. So we know where those thunderstorms are peaking, like in this middle picture in the lower bottom level. We're also able to detect wildfires from it as well, which is really key, that we're able to see maybe there's some lightning that caused some wildfires, and we can detect where that is. Another important tool with this satellite is it can detect lightning strikes, which is key to seeing where these thunderstorms are. So another great tool that we use. Again, here's another one, using the surface observations. Many of our sites that give us the observations at the surface are automated. Which is great because we can get some real-time information very quickly, but there are some things that it is lacking. These automated observations aren't able to tell us how big the hail is that's falling. They may tell us that there's hail, but we don't know how big it is. It surely can't tell us if there's any tornadoes or observe different cloud formations in the sky, and definitely can't give us any snow depth or snow information. So although it's a great tool, we still need more detail, especially with thunderstorm development, to get more information what's going on. We also use web cameras as well, which is great on seeing what the road conditions are like and what is going on at ground level when we don't have eyes on that spot to see what's going on. And then we have our high resolution weather models. So we have supercomputers that are able to run programs that model the atmosphere. And we've come a long way with our weather models. In fact, they're still improving constantly. They give us some really good detailed information on where we are thinking we're going to see thunderstorms developing. And we can get these updated every hour to give us give us updates, and many different types of models to give us different scenarios that could be happening. So we can look at all this information and sift through it to determine where we think we're going to see some thunderstorms developing. So these are all great tools, and they are improving year by year. But one thing that we can't improve on is getting the true report, the human report of what's happening beneath the storm. So that's why weather spotters are so important. We need to know what that ground truth is. We need to fill in those holes that maybe our tools are missing. We really need to know what is going on so we can verify these warnings and be able to do additional warnings based on this information. And also to provide credibility to the National Weather Service warnings and try to lead for public action. So all very important roles that a weather spotter does have. Okay, so with that, I didn't brief you on this one, but we're going to be testing you along the way. And I have several poll questions that we're going to be going through. So here we're going to launch our very first one. Let's see here. Why are weather spotters so important? So let me launch this for you. I'm going to give you some time to go through it. I know we covered some of this information, so you can sift through it, and I want you to pick which answer you think is the best one. So we're collecting that information, and looks like we're getting many reports coming in right now, so I probably don't have to wait very long on this. In fact, I think most of those reports, and I'll give you a little extra time on that. Okay. All right. Why are weather spotters so important? Okay, I think most reports are in, so I'm going to close it and share your answers. So yes, all of the above. Provide reports for ground truth for severe weather. That is very important. Fill in the holes that our tools aren't able to pick up from radar or satellite, and add credibility to the warning. So I would say all the above is the best answer for that. So great job on this. Okay, so let's go on to our next section. Weather hazards. We all know weather changes with the seasons. And as we go through the seasons, our weather concerns do change as well. I mean, we go through the winter season and we are focused on snow amounts, snow depth, ice, also strong winds as well. As we get into the spring season, like now, we're looking at the snow in the mountains and looking for those warm spells when that snow is going to come off, and then our concern switches to river flooding and also flash flooding with thunderstorms and heavy rain events. Also, when we get into the summertime, we kind of then shift our focus for fire weather, looking for those thunderstorms that may not be producing a lot of rain, but lightning. And then those dry, breezy days that could fan the fires for increasing some of the wildfires. But overall, thunderstorms, that's a key part, especially from spring through the summer and even into the fall season, where our concerns then shift for the severity of the thunderstorms, if they're going to be producing hail or wind, or how much lightning it is. And a lot of that has to do with the terrain. We live in a unique area, and the topography plays a big role in what type of weather that we see in our area. The Cascades, that's the spine of central Washington, it really separates the different climates from the marine type environment to the west to the dry continental environment to the east. And it also affects the precipitation, which I think is just fascinating that we see in this map, the average annual precipitation and how we can see amounts of 150 to 200 inches a year across the Olympics and the west slopes of the Cascades. to less than 10 inches in parts of central Washington east of the Cascades. So definitely terrain makes all the difference, and it does play a big impact on where we see storms and what type of weather that we see. So this also goes to our spotter reports and what type of information that we're looking in for a spotter report. And if you've attended these classes before, you know we have our Inland Northwest Weather Spotter Checklist, highlighting those top, more extreme events at the top, and then going all the way down the list, covering the gamut, not only with severe thunderstorms, but with wind and winter weather, along with excessive heat and cold as well. So we have quite the list of different types of criteria to look at. And then also with this weather spotter report, keep in mind the specifics on when you give the report. We like to know who you are. And with registered spotters, you will get a spotter ID. If you don't have one already, you will be assigned one once this course is done. Also, what you're seeing and where you are. So we can map that with our tools and determine what the storm is that's producing that. Knowing the times of things, estimates of what's going on is also key as well. And also knowing how certain you are of what you're seeing also helps us being able to determine what the confidence is on the report. So all very good things. Okay, the next poll question. We're going to go to what types of severe or hazardous weather do we not experience in the inland Northwest? So let's launch this one, and we're going to test your knowledge on this. Okay, I see the reports coming in. All right, I see them trickling in. Good job. Okay, I hope this one isn't too tough. I see things have slowed down a little bit, so we're going to close the poll and then share the results. And hopefully this one wasn't that tough. Yes, we see firestorms. Yes, we see flash flooding. Yes, we do see tornadoes as well. I know it's been a few years, but yes, we do see tornadoes. The number one type of weather we don't see is hurricanes. So great job on that. And why do we not see hurricanes? Well, it has to do with the type of environment that hurricanes need, which is warm ocean water. And that is one thing we don't have around Spokane or across the inland Northwest. So great job. We're going to hide that and move on to the next section. Spotter reports. How do we do it? Well, very easy. The easiest one is the phone number. And I have the phone number right there that you can jot down. I'll also be sending that to you later on as an email, but that's the easiest way to do it. Just call us on our spotter line. Tell us what you see, tell us where you are, and of course, what time it is. So we can map that with our radar and our other weather tools to see what we're looking at. Also, for those that like to be online a lot, you can submit weather spotter reports through the website. Just as easy, you just go to weather.gov, our webpage, and scroll to the bottom, and we have a little widget all set up. Submit a storm report, and this will allow you to put in the report, and you can click, 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 and just as easy, send the report right to us. So very, very easy way of doing it. Also, feel free on sharing your weather data on social media. We are active on Twitter, we're active on Facebook, And we look through these different platforms to gather the data. And especially during a severe or hazardous weather event, we're able to grab those reports. So if you want to share them on the social media, just tag us and we'll find them as well. Also, another way of gathering data is through the app called MPing. You can download that right on your phone, and it's a crowdsourcing app. So it allows you to report the type of precipitation falling, which I find really handy, especially in the late winter, springtime, when we're not quite sure if it's falling as snow or is it falling as rain or maybe a mix. So you're able to put that in the app to report what type of precipitation you're seeing. Also, it has different options to include wind information, wind damage, flooding as well. So it's really easy to use, and we're able to download that data and be able to look at that on our workstations. Also, email, very, very key. If you want to share any types of report via an email or pictures, please send it to the nws.spokane account. That will go to anybody who is working the forecast desk, and they can get it in real time. Sometimes I get reports sent to my account, which I will just forward to the office, but I'm not always in the office, so sometimes I may be slow on seeing the reports. But if you want to get those reports in right away, I recommend using the office account to send those pictures in. And we enjoy getting them. This is great reports that we get that way. And also, if you are a ham radio operator for the hams out there, we have every county has set up some maybe ham radio networks or Aries Races networks that you can join in and share that information and get it collected to send to our office as well. So as I mentioned, emails are very important. Sending information to our office account, but also keeping us current on your contact information, especially your email. Phone numbers are key, but also emails, because this is a great way that we can keep a dialogue going and keep you updated on things, especially if we're going to be seeing a widespread severe weather event or a high-profile hazardous weather event in the wintertime. We could be sending out an email to you to get you prepped and get you ready for an event that's going to be happening. Also, we send periodic emails to include our newsletter that is for all of our weather spotters and observers in the region, that gives you data and climate information and outlooks for the upcoming season. Also, keep in mind that we may be calling you as a registered weather spotter. We will be gathering your phone number, and if we see an event near your area that we would like to get a report on, we will call you when it's safe to get those reports. So just keep that in mind. We'll be contacting you for ground truth as well. All right, here is the next poll question. What would be your preferred way to send reports to the Weather Service? Now, there's no wrong answer to this. We're just seeing how people would prefer to send in their reports. Like I said, you can call the office. You can send it online. You can, if you're a ham, you can send it through the radio or email. So we have lots of different options that you can use to send the information in. We just like to see what people prefer. Oh, I see the reports are coming in. Okay, I think most of them have come through, so I'm going to close and share the results. Oh, this is really interesting. So we see the majority of people would like to send the reports online, 36%. And then 28%, it's kind of a tie between calling the office and emailing the office. So great. Oh, it does look like we have some hams out there. So great. Yeah, sending your reports through amateur radio. So terrific. Terrific. Okay, so we're gonna close that and go on to the next section. So now we're going to talk about thunderstorm hazards and go into a little more depth on the ingredients for thunderstorms. So for thunderstorms to develop, we need to have just the right types of ingredients in the atmosphere for this to happen. And these are the main ingredients. It includes moisture, lift, instability, and also wind shear. So let's dive into this a little bit. So ingredient 1, moisture. So that is just simply the water in the air. And we all know with water comes in different phases, liquid water, solid water, but then we have water vapor. And water vapor is the fuel that thunderstorms need. And it's what makes the clouds and the precipitation. And our sources for water vapor being east of the Cascades, it's a little limited compared to the west side. But we can get moisture that comes in over the Cascades and spills into the region. We also can get it coming in from the south. Southerly flow can bring in moisture into our region. And sometimes, believe it or not, we actually can get some moisture that comes in from the Gulf of Mexico and swings up. We would call it more of an easterly flow that moves into the area. So those are some key moisture sources. Yeah, so that flow that comes from the south, that's the monsoon moisture that we see that just kind of creeps up to our area. So the tools that we use to monitor the moisture, a big one is satellite, the water vapor channel, which is the one that's kind of shaded with orange and green. The green would be indicating high levels of water vapor, while the orange is showing us the drier areas, but we can see how the flow is moving into the region with that. We also can determine the moisture in the air by our weather soundings. Because we're able to measure the moisture and it shows up with the dew point in the weather sounding. So it lets us know how much moisture is within the column of the air, along with our surface observations as well. That dew point is really key. Higher the dew point, the better the fuel is for thunderstorms. So those are some important tools to keep in mind. Also, relative humidity. That is the measure, the percentage of moisture in the air. So when it's high, that's good for moisture in the air. All right, our second ingredient is instability. And instability is more of that energy that's needed for thunderstorms to develop. And it helps the atmosphere mix naturally. So it also is a good example is talking about density of the air. We find that with different temperatures of the air, they behave differently. So cold air masses, they tend to be more dense and they want to sink. Warm air masses are a lot lighter, like a helium balloon, and they want to rise. So if you can get those air masses set up that we get warm air near the surface that wants to rise and cold air aloft that wants to sink, we can get the whole air column, the air to mix, which is terrific for increasing that energy for storms to develop. The opposite of that is what we see, I would say, more in the wintertime, where we have cold air near the surface and warm air aloft, and that's more of a stable environment. And like we see in this lower right-hand picture, that the air doesn't mix and it just kind of flows flat. And those are the days that we have our stratus, our fog types of conditions. For unstable conditions, we want warm air near the surface, cold upstairs, and that air mixing and rising. And those are the days that we see more of our cumulus cloud development, the puffy clouds developing that then can turn into showers and thunderstorms. So again, the tools that we use to monitor that, again, are weather balloon soundings. Those upper air soundings will let us know where those warm pockets are, where those cold pockets are, along with what's going on at the surface. And some terms that we use to talk about instability include CAPE. You'll see that and sometimes in our discussions that we talk about, lifted index, and lapse rates. And lapse rates just has to do with the how unstable the atmosphere is and changing temperature over height in the atmosphere. Another key ingredient for thunderstorms is a lifting mechanism. It's something that's going to trigger, it's going to push that air up to develop into the thunderstorm. So it's going to force the air up because sometimes it just doesn't do it on its own. We have two key areas that are great lifting mechanisms in our region. One of them is all around us. And like I mentioned, terrain, the topography is a big source for triggers, where we have air that is forced up the slope, and this forces the air up that we see clouds forming on the windward side, and if it's unstable enough, it can develop up and develop into a shower or a thunderstorm. So terrain, the mountains are a key trigger for lifting the air. Another one is a cold front. So it's air that's forced up by a frontal boundary. So cold fronts are invisible. We don't really see it, but we can visualize it with the air flows on weather maps, what the winds are doing, and especially what the temperatures are doing, where we have the clash, the boundary of the air masses. And with that, with a cold front, we have the cold air that moves in, forcing warm air up into the atmosphere. So the ways that we monitor, the tools we monitor this include satellite and radar, along with our upper air and surface observations. And terms that we use to describe this can include vertical velocities, what's going to lift the air up. Vorticity is another term that we like to use, and fronts, talking about where the fronts are in the atmosphere. And the last ingredient I want to talk about is wind shear. And this is something that helps more determine how severe the storm is. Those first three ingredients are needed for general thunderstorms to develop, but that fourth one helps us tell if the storm is going to be just maybe your garden variety thunderstorm, or are we looking at a complex supercell development. And what wind shear is the change in wind speed and direction with height. So we know that we can have winds that are changing near the surface, but if you think vertically, they could be increasing with speed and changing direction with height. That would allow storms to grow. And one good example has to do with rolls in the atmosphere. So there's different movements going on in the atmosphere, these horizontal rolls, where if you think of like playing with a piece of Play-Doh and making the big long snake with it, as you're rolling it in your hands, you're making a roll like that. And these form naturally in the atmosphere. But if you get one of those rolls developing near the surface that's beneath a developing thunderstorm, what it's going to do is pull that roll vertically and make these tubes that extend from the surface on up that help support the rotation in the storm. And that rotation is key if we're going to see a long-driven thunderstorm that can produce a lot of severe weather. So again, we monitor the environment for wind shear by looking at what the radar is showing, because with the Doppler radar, we can pick up wind speeds and velocities, also from our upper air soundings and the surface observations as well. And some terms that we talk about when we're looking at wind shear include what the shear is, helicity, and hodographs. And that's where we're looking at the changes with wind, with height. And here is an example right here that does show a hodograph, so that a graph that shows the changes in wind with height. So here's a little chart that we talk about the basic thunderstorm elements and what we need for the different parts. So as with the shear, that's the change in wind with height. It helps storms become more organized, and we see this common ahead or along a front. For the lift, that's that lifting mechanism that's going to force air up, and it's going to create a focus where storms are going to develop. And like I said, they could be cold fronts, warm fronts. It doesn't list mountains, but that's another key one as well. Here's the instability. That's the energy for thunderstorms. And that is where we see the warm air rising and the cold air sinking, and very important for providing that energy for storms. And then moisture, obviously we need that. We need the precipitation, the clouds to form, and important tools are just monitoring that dew point and that relative humidity. So here's an example of with Thunderstorm Basics, with the different parts of the thunderstorm. With the thunderstorm, you're going to have an updraft part, and where you have air rising up. And in this updraft part, you're not going to see much in the way of precipitation beneath it. You're going to have a rain-free base. You're going to have cumulus clouds developing with it as well. So we're not going to see much in the way clouding that base. So we know that's the updraft portion. The downdraft part is going to be actually on the front side of the storm, where it's darker and looks angry, I think, as I call it, where we have the rain coming down, where we have the downward motion. And this is also where we're going to have the strongest winds and hail as well. And the leading edge of this is noted as a shelf cloud. So it's the leading edge of that downdraft of the storm. So what makes a severe thunderstorm? Well, simply it's looking at the size of the hail and the speed of the winds. And what the Weather Service has determined, winds that are greater or equal to 58 miles an hour, or any severe wind damage. 58 miles an hour also equates to 50 knots. So when we get winds that strong, it's considered severe winds. Also, hail is another one too. When you have hail that's bigger than 1 inch, so quarter size or bigger is what we're looking at for severe hail. And if we get any reports of tornadoes, well, obviously it is severe, but with a tornado report, that's when we are looking at the next step with a tornado warning. And we can have a severe thunderstorm with a warning, and also a tornado warning with the same storm as well. But keep in mind that not all thunderstorms are severe. Less than 10% of thunderstorms are severe, and that all thunderstorms produce lightning. Now, lightning doesn't really determine that a thunderstorm is severe, but it is extremely dangerous, and you need to be safe when there's thunderstorms around. So just keep that in mind of your safety. So we've been keeping track of thunderstorm data year by year for our area of the inland Northwest. And here's a little graph that shows, actually it goes through, I think we have it through maybe 2019. There's a couple years we still need to tack on to that. But you could see year by year how our severe reports reflect. And that we have some quiet years and we have some very busy years. Our most active years was 2012, 2014, and also back in 1997. Looking back at just last year, 2021, we did have 6 thunderstorm warnings that were issued that year. That seems a little low, but we did get over 30 reports of severe weather with those storms warnings. So that is terrific that we're getting that many reports. Also want to keep in mind that 1995 was when the Doppler weather radar was installed and turned on, and also when the office in Spokane was gearing up and watching more for severe weather. So although we had a lot of reports back in maybe the late 80s, things were a lot less active, partly because we didn't have a radar in the area, and maybe our spotter network just wasn't as big at that time. Now, if we look comparing it, these reports by month, we see that the peak month for damaging winds and hail is oddly in July. That's when we see most of those reports, while the peak month for tornadoes is actually in May. So there's a little disconnect with that. And also that we've had severe reports all the way stretching in January and as late as November. So December is the only month that we haven't had reports of severe weather in our area. And the most active time of the day, well, not surprising, it is mid-afternoon to mid-evening during the peak time of the day and the peak heating of the day that we see most of this activity. Less activity in the morning, but we still see it. And that we can get those wind reports continuing through the night. You know, that's the orange bar, and we see how they still continue even into the early morning hours with some thunderstorms. Okay, here's the next poll question. What would be a good ingredient for thunderstorm development? So I'm going to throw some terms out there that we were talking about. So one of them has to do with high precipitable water. Would that be a good ingredient? Would low dew point be a good ingredient? What about high lifted index? I know that one's kind of tricky. Lifted index, and then high pressure. What would we be looking at? What would be a really good ingredient that we need for thunderstorms? I see lots of the answers going in here. Okay. All right, I see those reports coming in. I know this might have been a little tricky, so I'll go into more explanation after here. Okay, so we're going to close the poll and share it. So we kind of had a little difference here. Nobody said a low dew point, so that's correct. We had a few people thinking of high pressure. Well, actually, we want low pressure for thunderstorm development. So, because high pressure actually would make skies cloud free and not really conducive for thunderstorm development. The actual real true answer is a high precipitable water, and I guess I should have explained more about lifted index a little bit more, but actually with lifted index, we want lower levels of it. In fact, we want negative values of a lifted index to determine how unstable the atmosphere is. So kind of measures how unstable, like with the lapse rates are. So ideally we want low lifted index and high precipitable water. So good job on those answers. So we're going to hide that. All right, we're going to talk a little bit more about the types of thunderstorms. They come in 3 different flavors, as I like to call them. Our general garden variety thunderstorms is called the single cell. Those are the ones that just kind of develop up and they come back down. Then we have the multicellular. So there's a little more organization with the storms, and we have them developing along a line. That could be storms that may be redeveloping in the same place over time. So a little more organization with that. And then we have our supercell, which is our massive thunderstorm that's rotating and producing a long stretch of hail, damaging winds, and even tornadoes with that. So here is a single cell thunderstorm and a little picture of that, a little video going. So what we have is the cumulus cloud developing. We have the updraft going up, straight up, develops the cell. When it reaches its peak, then the downdraft kicks in. It comes right back down, and it actually just shuts off the updraft. And then the storm just kind of falls apart. So the typical life cycle is 30 minutes or less. We can get some severe weather out of it. It's really short-lived, like a burst of it. But most of the time we get small hail and some gusty outflow winds with that. So they're very quick storms, and we could get them developing over different areas, especially mountain areas where we get on the windward side, them developing. So we get the little bursts of weather with that. All right, so with these, we can get heavy rain from them. And when we're looking at heavy rain, we're looking at, for convective heavy rain, getting a ½ inch of rain in an hour. That is some heavy downpours. Even if we're getting maybe an inch over 12 hours, now that's more for our steady rain, or maybe an 1.5 to 2 inches over 24 hours. We like to get those reports too. But when we get from thunderstorms a ½ inch of rain or more in an hour, that can lead to some issues like we see here that happen here at Omak, leading to flash flooding, debris, mudslides with that. Also hail. So hail can come in many different sizes. With your general thunderstorms, you're going to get small hail. So for measuring hail, there's good ways of doing that. Using coins is highly recommended, from a penny to nickel size. That would be small hail. You can also, if it's really small, use pea size as well. But once you get to quarter, you're into the severe hail, and on larger, using different ball sizes, from golf balls, pool balls, baseballs. Yes, I did hear of a thunderstorm producing CD or DVD size hail, which is very large hail. How hail forms is within the thunderstorm. If in the updraft, it pulls up you have a little piece of ice in the upper parts of the thunderstorm. It wants to fall down through the downdraft, but the updraft will grab it and push it back up in the storm. So it rotates through these convection currents. And with each time it rotates through, it gets another layer of ice. So with the stronger the updraft in the storm, the bigger the hail. So the hail's not going to be falling out until the updraft can't keep it aloft in the storm. So with that, when we get very large reports of hail, we know that is a strong thunderstorm. And here are some examples. We can have the size of the hail being quarter size or bigger, but also we can get a lot of small hail, like we see here in Medellin, that cause a little pile of hail. Ideally, what you want to do is measure the hail with the ruler. If you don't have the ruler, a coin works, or balls, to determine how big across the diameter of the hailstone is. Damaging winds is another key one from thunderstorms. So with your single cell thunderstorms, there'll probably be some brief gusts. You could get some severe winds to 58 miles an hour, but you typically would need some stronger, more organized storms produce higher winds. But we can get winds from downburst winds, also from sustained winds that we see even in the cold season as well. But definitely damage to trees and power lines are key. And some of you may have weather stations set up that you're able to get a wind measurements, but most probably don't, like myself. So I need to be able to estimate what the winds are doing. And a good tool to use is the Beaufort wind chart. It's great on estimating winds just by looking at what the branches are doing in the trees or what a flag is doing, and describing the winds as a gentle breeze to fresh breeze to near gale. And this is a great way of describing what the winds are doing. And if you're able to give that type of report as a spotter report, that's terrific. When we get a lot of winds from a thunderstorm, especially those strong outflow winds, it could lead to blowing dusts, and we could get dust storms with that, especially if it's been really dry and we have some agriculture plowing of the fields nearby. So that's a source region for the dust and the dirt in the air. So sometimes we can get that developing, these dust storms, when we get thunderstorm events. All right, let's talk about the next type of thunderstorms. These are the multi-cellular thunderstorms. They have a little more organization with it, and this has to do with the wind shear. So we have a little wind shear going on that allows the updraft of the storm to continue while the downdraft is falling down. So you may have the storms propagating or moving in one direction, and then they're developing on the back side. So it kind of looks like the storm isn't moving. It's staying in one location and producing rounds of heavy rain and hail and gusty winds with that. But when actually you're just getting multiple cells developing in a line that are continuing to develop. So this type of environment scenario can lead to these strong downbursts and straight line winds and the larger hail as well. Not much in the way of tornadoes. It can happen, but more of the heavy rain that can lead to flooding is another concern. So here's an example of a downburst straight line winds. So this has to do with the downdraft of the storm, and which can lead to either a microburst or a macroburst, depending on the size of that downburst. So what it is the rain cool air from the thunderstorm dropping down to the ground. And remember, we were talking about the density of the air, and when it's cold air, it wants to sink down. So it drops like a rock in the storm, straight down and spreads out. And this can cause quite a bit of wind damage as that air drops down and spreads in all directions, that evaporative cooling, and can cause wind damage to trees and structures with that. And also not good to be, if you're a pilot, you want to stay away from these types of areas with that. So another concern with these multicellular storms is flooding, because we get heavy rain that continues in an area over and over again. We call this training of this training cells, where they continue in one location and keep producing rounds of heavy rain. So this can lead to flooding, specifically flash flooding. So flash flooding is when we get flooding within 6 hours. So it's rapid rises on rivers, on streams, and in low-lying areas. So if it's happening in your area, giving specific locations is key. Roadways, intersections, streets, also streams as well. And we've had cases of flash flooding in many areas, especially urban areas where we have a lot of blacktop, a lot of concrete where the water just can't soak in. So it leads to flooding in these low-lying areas. Oh, I have a video here that shows a flash flooding event. This happened several years ago in parts of north central Washington, I believe, but it shows the power of water. And you can see how fast that water is moving. It's moving very quickly and can cause quite a bit of damage. I would not want to be that close to water that's flowing that fast. One wrong move and you could get swept away. In fact, it only takes 6 inches of moving water to knock a person off their feet. So I hope that gentleman there moves away quickly. Also, you don't want to be driving through water like that. All it takes is a foot of moving water that can lift a vehicle off the pavement and move it downstream. So it's very important to be alert of flooding and not get caught in it. Likewise, we have another concern with our area having to do with the varied terrain, the steep slopes, and also burned areas, as we call burn scars. When we get a thunderstorm that produces heavy rain in these areas, it can lead to a lot of increased hazards, including not only flash flooding, but mudslides and debris flows. And with debris flows, think of it as a slurry of water and rock and mud that's moving down slope. So when we're looking at burn scars, these burned areas, especially the more recent ones, when we have a intense fire that burns the soil along with the vegetation. It bakes the soil. So when we get rain that falls on these areas, it doesn't soak in. It wants to just ride over the surface and down the slope. So it can lead to an increased threat of flash flooding. It can pick up dirt and mud along the way and also trigger debris flows. So this is a definite concern if you live down slope of any areas that have been burned or are traveling on roads that are near these areas. So these post-fire floods are a main concern, and definitely after the active year we had last year, we are keyed in on these areas for this upcoming season and the years to come as well until they can recover. So getting reports of this is key. Just like flash flooding, knowing specific locations, roadways, intersections is very important. Now here's another type of thunderstorm. This is the supercell. This is the rotating column of rotating thunderstorm. So it has high amounts of wind shear in it. Also, these are the types of storms that would be producing our thunderstorms, our tornadoes. And that's because they're rotating and producing hail, heavy rain, wind, and the risk of tornadoes increases. And that's because with this rotation, it allows the thunderstorm to continue to develop and allows the updraft and the downdraft to remain separated and allows it to last for an hour or even longer. And there's some key things to look for when we're looking at a well-developed thunderstorm. We're looking at the overshooting top. I call it the cauliflower on top. That's bubbling up as it's getting to the top of the storm. The cauliflower shape on the sides that looks very bubbly as it's building up. With these thunderstorm clouds, these cumulonimbus, they can rise about 2 to 4 miles high. So they're massive clouds and all that development going on. Also, another key with supercells is that rotation area, the mesocyclone of the storm. And that's where we find that at the interface of the updraft and the downdraft. It's a lowering of the cloud base that is circular and rotating. And that would be the area to look for any funnel development, any tornado development. So this is called the wall cloud of the storm. And compared to the size of the storm, it is quite small because, like I said, these cumulonimbus clouds are huge. And you want to look beneath there at that rain-free base to be able to see that rotation taking place. So just a reference of different types of cloud types. It can be a little tricky when you're watching clouds and looking at trying to key on the ones that would be the severe signals to look for. So here is one type of cloud. They're called Scud Clouds. We would see them beneath showers or thunderstorms. They look pretty ragged. But no, this is not a sign that there is a funnel developing, partly because it's so ragged. When we are looking for a funnel developing or rotation, it's going to be smooth. It's going to be smooth and moving. So Scud clouds are not good signs for that. Stratus clouds, they're the stable flat clouds. Also not a sign of thunderstorm development. We'll probably see them after the event when things stabilize and maybe we get some fog developing, but definitely not a sign that there's thunderstorms nearby. A cumulus cloud. Yeah, that is the sign that things are starting to bubble up, starting to develop. But at this stage, no, not a sign that we have a thunderstorm. We may in the future, but not at this moment. Seeing a thunderstorm, a cumulus starting to bubble up as this, a towering cumulus stage, this would be the starting sign of seeing a storm develop. So we're getting that updraft developing. We're almost getting to that peak that we would be seeing the thunderstorms develop. So this is a good sign to look for. Another one would be Mamatis Clouds. So this would be more on the underside of the cloud where we would see some protrusions coming down. That's a good idea that we have a lot of development going on within the cloud and a sign that we could see some severe weather possibly. And also the wall cloud. So here we see a picture of one. I know it does look a little ragged on the edges, but overall, it does look, most of it looks fairly smooth. So this is what we want to keep our eye on and see if we see any further development going on with that type of cloud, especially if it's in the right spot beneath the thunderstorm, between the updraft and the downdraft of the storm. So having to do with tornadoes, yes, we do get them in the inland Northwest. On average, we get 5 or less a year. They are fairly small. Climatology shows that they're usually on the ground less than 5 minutes, so they're quick. They're about 100 yards in diameter, maybe last a quarter mile on the ground, and they're mostly on the wind scale, an EF0 to an EF1, so fairly weak. And keep in mind the definition of a tornado is a violently rotating column of air that starts from the thunderstorm and works its way down to the ground. And what you want to be looking for is the debris cloud. So we want to see it picking up dust and dirt at the ground level. So these examples show some debris, that funnel coming down, and look how smooth it is, that funnel, how smooth it is, that you can be able to pick that out. Especially this one here, the far right one, you can see that debris cloud. It may not be visually connected, but if you can see debris on the ground, that is key that you have a tornado. Here I have a video of one from several years ago of a tornado that was right near Airway Heights. This is the Northern Quest Casino right in the foreground. But if you look here at the top, you see that funnel. You see how smooth it is. So this is where you'd want to be keeping your eye on it, that, oh, there's a funnel, and you want to look down, and definitely we have a debris cloud taking place near the surface with that developing. So it's not quite connected, but give it time. If it lasts, we could see them join together, but definitely enough force to kick up that dust and dirt and cause debris. So how tornadoes are measured, as I mentioned, it's the EF scale. It's called the Enhanced Fujita scale that goes from 0 all the way to 5, with EF0 starting at wind speeds of 65 to 85 miles an hour, which is as fast as we would be on the interstate at times. But as we go up in number, we see how those wind speeds increase. And with each scale, we hit more damage with that, more damage to structures and vegetation and trees with that. And here's a map that shows the average annual number of tornadoes per state. And this goes back from the mid-80s into the 2014. If you look into the inland Northwest here, I said 5 or less. Well, I'm including Idaho and Washington on average for the inland Northwest that we see 5 or less tornadoes a year. But what really draws your eye, I'm sure, is where Tornado Alley is, from Texas all the way up to Oklahoma, Kansas, Colorado, Missouri, Nebraska. This is where we see the bulk of the tornado development each year. On average, the United States sees over 1,000, actually 1,200 tornadoes each year. And it is 4 countries sees the most tornadoes than any country in the world. And that's because all those ingredients come together just right. So here's some stats for tornadoes by reports going all the way back to the mid-1930s. Quite a bit of data. We've had 64 reports of tornadoes in our area in that time. And by the time of the day, looks like afternoon into the early evening is where we see the best chance of tornadoes. By month, we kind of mentioned that already. The peak month is May, where we've seen 21 reports of tornadoes in our area. And by rating on that EF scale, the majority of them are EF0 and then EF1. But believe it or not, we had an EF2, actually 2 of them in our area over that time period. And here's a map that shows the tornado tracks that have taken place. This stretches back from 1950 to 2017. This is from the Climate Center in the MRCC Climate Center out of Illinois. But it highlights in blue what those EF0s were and the storm tracks. In green, what EF1s were, and EF2 is in yellow. You can see some of them had some little storm tracks here to the east of Lewiston and down in Northeast Oregon. And then that sole EF3 right here that was west of Spokane. So yeah, really exciting to see where the different tornadoes have been across our region. So I get this question a lot, talking about tornadoes versus funnel clouds and then the dust devils. What is the difference between them? Well, we talked about tornadoes. So it's that rotating column of air from the thunderstorm to the ground, and that you need the debris cloud. So before we get that debris cloud, before we know it's on the ground, when we see the funnel, it's when we call it a funnel cloud. We don't call it a tornado until it touches the ground. So that's what the difference between those two are. Now, a dust devil, a little different. Sure, it produces quite a magnificent funnel, but usually those happen without a cloud in the sky, or maybe very few clouds. And these develop from heating near the ground, as we talked about those horizontal rolls with wind shear going on. Well, that's happening in those farm fields on the sunny day where we get a lot of heating going on near the surface. And if we get any type of development to push that roll up in the vertical, it can start spitting and pick up some dust and dirt and produce a dust devil. Winds with a dust devil are quite a bit less than a tornado because it doesn't have the support of the thunderstorm above. Sometimes we can get a dust devil that develops, maybe with a cumulus cloud as well, and they can come together and maybe produce a very weak tornado. A lot of times we call these land spouts because they're very weak and hard to see on radar where these develop. and can produce some minor wind damage. So ideally, if you can pull out your phone and take a picture of it, that's great, and share that information. But definitely there's different types of scenarios that can produce the funnels in the sky. And I also want to point out with funnels, sometimes we can have a bout of cold air funnels happening in a particular area. And back in May of 2020, we had that around the Pullman area, and along with in Ritzville as well, that we were getting several reports of these funnels happening from the sky. And this was an event that was happening that we had very cold air aloft. So remember that instability going on? So we had cold air aloft, warm air at the surface, and it was the right conditions to be producing these funnels developing, but the storms were very weak, and the funnels weren't reaching the ground. So they were producing some very amazing pictures with that, but little damage happening with it. Okay, here we go. We're going to be playing Let's Identify the Clouds. So let's try this one. What do you think this cloud is? We're looking at, is it a cumulus cloud? Is it B, a wall cloud or mesocyclone? Is it a Mamatis cloud? Or is it a lenticular cloud? Now, I didn't really talk about lenticular clouds, but these are, lenticular clouds are clouds that develop over mountain ranges that are very smooth and sometimes look like UFOs just because of the winds flowing over the mountains. So I would not mention a lenticular cloud on this one. So we can try a different selection on that. But I see the reports coming in right now, and I think this is great, seeing what people are thinking. It's definitely an unusual cloud, and I would be wanting to watch this for sure on this. Okay, we're going to close it and share the reports. All right, the majority of people say that this is a wall cloud or a mesocyclone, and I would agree, yes. If we'd be watching this, I bet we'd be seeing some rotation going on with this. True, there would be a cumulus cloud going on nearby. It's probably more of a cumulonimbus going on with this type of development. So we would want to watch that. So great job on this. So let's hide that. And here, another question. Identify this image. So let's try this, and we're going to launch it. So what do you think? Is it a shelf cloud? Is it cloud to ground lightning would you be reporting? An approaching thunderstorm? Or would we just report all of them? Yeah, there is a lot going on, and I have to say this is a fabulous picture too. So thankful for the weather spotter who took this to share it with us. But yeah, we have a lot going on in this picture. So I think it's pretty much safe to be able to share this by now. Majority of people say all of the above would report this, and I agree. Because the cloud formation shows an approaching thunderstorm, because this would be a shelf cloud. So we know this because we see the downdraft happening behind that. And also the cloud to ground lightning going on as well. So definitely know that we have thunderstorm activity going on. So terrific job. Okay, so let's talk about different ways to stay informed. As weather spotters, you're probably really tuned into weather and weather enthusiasts and like to see where thunderstorms are going to be developing. Well, on the web page, you can go to the National Storms Prediction Center, spc.noaa.gov, which is a great source to see where you can monitor thunderstorm activity going across the country and look for the outlooks that they post on where they are monitoring for thunderstorms. So this office in Norman, Oklahoma, that's all they do is look for where thunderstorms are going to develop. So that's what they concentrate on. And they have a code on understanding the risks for thunderstorms, starting with just the pale green that we see most of on just general thunderstorms, and then highlight the severity of the storms, going from isolated severe to scattered severe, numerous, widespread, or high widespread activity expected. So this gives a good range on what type of thunderstorms that we could be seeing in different areas. So definitely an important site to monitor. And then it's our webpage. It's also a good source as well at weather.gov/Spokane. There's lots of great things that you can monitor, including the current hazards that I think we do have SPC linked to it, so you can see what that thunderstorm risk is. Also, you can look at radar data and the forecast computer models. So you can look at some of those high resolution model outputs and see where the models are reflecting on some thunderstorm activity. I'd also want to point out ways to also keep an eye on what the river flows are doing during high flow events as well. And then if you would scroll down to the bottom of our page, we have lots of little widgets set up that allow you to look at our area forecast discussion, so you can see what the forecasters are talking about or suggesting what the weather hazards are. Another way of getting to the radar and satellite images and current observations and what's going on in our region. But more importantly, where you can submit your spotter report. If you like to do them online, there's the link right there. And then also to view the storm reports. So when we get severe thunderstorm reports coming in from weather spotters, we are able to push those out as a local storm report and share them with the public and the media. So your reports are key on not only verifying the warning, but also we share them online, and you can see the different reports coming through through our local storm reports. So here I'm also going to touch on some basic radar interpretation. So if you're going to be looking at our radar online, we have an updated radar page that gives you lots of selections that you can pick to look at different parts of the radar. And some of the main ones I'm going to talk about is reflectivity, velocity, and precipitation amounts. So with each slice of the radar that goes through the storm, we're getting updated information in all these levels. So what is reflectivity? So that's basically the intensity of the storm. It's how reflective those targets are. So the blue, the green levels, that's pretty small. For precipitation, very light amounts. But as we increase from green, yellow, red, purple, we're getting to bigger drops or ice, hail happening. So when we see them turning red to purple to white, there's a really good feeling that there is some hail going on within the storm. So we measure it in a dBz form, that's the unit, and we can look at it as a base reflectivity, which has to do with what tilt we're looking at. So with the tilts, they go up in elevation from a half of a degree up to 1 to 1.5. So you have different tilts to look at. Or you can look at it as the composite, which is basically looking at all of them and you see the worst of all the slices for the composite. So we get a new image. The cycle repeats itself every 5 to 8 minutes, and then it starts it up again. So when we loop these images together, we see the progression of the storms and able to get this little movement. So we know if the storms are increasing in development, decreasing, and how the storms are changing with time. So velocity is another key part. And there's different types of velocity we're measuring within the storm. So we're measuring the speed and direction of these targets, whether it's rain or snow or hail or even debris going on that the radar is picking up. And it's measured in knots. And one thing to keep in mind that we're measuring the wind direction relative to the radar site. So when we see reds, it is movement that is outbound motion, so away from the radar. Green is inbound, so that's motion toward the radar. So we're able to look at a lot of these signals and monitor them at each slice, which is the base. So what that is relative to the radar. But then that's really good seeing of a storm that's producing straight line winds. But we're also able to look at these wind directions relative to how the storm is moving. And that actually helps us see if there's rotation going on in the storm, and helps us determine if we could have a storm that is a supercell and could produce a funnel cloud or a tornado. And another very important radar product is the precipitation products. And this gives us estimates of how much rain is reaching the ground. Now, these are just estimates, and sometimes we can have them overestimate the amount, especially if we have a lot of hail within the storm, because it can give us higher amounts than what's really happening. Or we can have an underestimation, especially with those distant storms. May not capture the whole column of the thunderstorm, so we might miss some of that data. But we're able to get measurements of precipitation on an hourly basis, which is really key for monitoring for flash flooding, or the storm total, so the amount of precipitation from the entire event. So very important information to help us monitor where we can be anticipating heavy rain and the possibility of flash flooding. But there's other different types of products available as well. With our radar, where we can get an estimate of the type of precipitation that it's producing, whether it's rain or snow or hail. We can get the tops of the storms, which is really key on how strong or severe the thunderstorm is. And then we have a measurement called the vertically integrated liquid, which is the short acronym is VIL. And that gives us an estimate of how much liquid is in the storm and an estimate of how much hail it could produce. So lots of different products to view. Another key thing to keep in mind is the time, and understanding that GMT time, the UTC time, or otherwise known as the Z time, and how that's different from our local time. For weather products, we follow that UTC clock, and that is so everybody all across the world can be on the same clock. Our weather models are also done on this clock as well, where we get the bulk of our weather models happening both at 0 Z, UTC, or 12. They're the most common types for our weather balloon launches, our weather models, and important weather data. And locally for Pacific time, for reference, 10 a.m. is roughly 17 UTC in the daylight time, and 10 a.m. in Pacific Standard Time is at 18 UTC. So you can see how there's a little difference in the time zones on that. So 0Z is actually in the evening time, 12Z is in the morning. So lots of good information on there. So here we're going to show one more poll question. What are some useful radar products? And some of them that I talked about. Reflectivity, velocity, precipitation products. We covered a lot of them, but I see most of you have agreed that all of the above are key, because we're looking at different parts of the storm, and reflectivity, velocity, precipitation are all very important. So I'm glad that I'm seeing that most of you got that point across. All of the above. So good job here. All right, we're going to hide that one. And I'm looking at the clock, and I'm seeing that I'm reached the 8 o'clock time. So we're going to step through these pretty quickly, but I just want to address how important it is to be safe, especially when there's thunderstorms. We want to keep in mind that the number one threat for during thunderstorms and weather spotting is driving. And just know that if you're really key of what's going on in the atmosphere with the storms, you may not be watching what's on the road. So it's important to keep that in mind. And sadly, it just this last week, we had 3 University of Oklahoma meteorology students that were storm chasing that were killed in a traffic accident. So it can happen, and it's very sad. So I just want you to be safe out there and understand that we have to keep our eyes on the road as well. So be safe on the roads, and also with lightning. Now remember, every thunderstorm can produce lightning, and it is potentially dangerous and deadly. So even if you're out watching a storm, be in a safe place, either inside looking at a window or within your vehicle is safe as well. So seek shelter, and remember to remind your family that as well. So if you're close enough to hear the thunder, you're close enough to be struck. Also, with heavy rain, standing water on roads is a big concern. Hydroplaning. So we want to keep our speeds at a conservative pace when there's thunderstorms in the area, and keep your headlights on as well. Be extra cautious at night, because it's really hard to see the hazards, especially flooding, any wind damage that has caused trees to go down, power lines. You have to be very, very careful during the night. And with storm damage, when we do have trees blown down, power lines, that is a hazard. And I know we want to get the crews in there to try to get the power back and remove the trees. So we don't want to get in their way, but getting some of those reports is important, but we don't want to get in the way of those that need to get rescued or get the cleanup underway. So it's important to be responsible when you're a storm spotter, and you're doing this right now by attending classes and sharing this information with your family and friends. And you can also learn more by other opportunities for additional training. We have spotter resources through the MET-Ed site. I have those listed on our webpage where you can get additional training, more about being a skyward spotter and convective basics. That's going to go into even more detail on thunderstorms. And then there is the Jetstream Online School for Weather, which is another great source with talking about different ideas and areas of weather. So here's our last question I want to talk about. What would be a safe weather spotting scenario? Just to reinforce, safety was very key. Would it be safe to be driving around at night looking for damage? Would it be safe racing your vehicle through water-covered roadways? Standing on a hill, watching the thunderstorm come in? I know that sounds so exciting if you love thunderstorms, but is it safe? And I see many of you got the message about being safe. So yes, going to close that one and share it. Being safe means staying inside and looking for the damage when you're done. So great job on that. Okay, one thing I just want to wrap up with is just seeing what our seasonal outlook looks like as we go in the next months to come. But first, let's talk about what happened so far in 2022. We've had quite a unusual start of the year for weather. Remember, January, it was wet for the first half, and then things kind of stopped by February. It was pretty dry and uneventful and cool. And then March, well, it stayed kind of dry. We had some small snowstorms, but it stayed kind of mild. And then April, we had an April surprise after April Fool's Day where it turned cold and got somewhat wetter. So overall, we've seen many of the lower elevations stayed much below normal for temperatures, while the mountains actually stayed above normal. And precipitation, it's been a roller coaster. Things overall look pretty good for the Cascades, a little above normal, and parts of the northern panhandle, but unfortunately, it's been somewhat on the drier side for north central and parts of northeast Washington. So we're going to have to keep our eye on that on the months to come. But thanks to our surprise April, we actually had mountain snowpack that was still building through the month. So far for May, it's remaining cool. We have snowpack that is above normal in most areas, which is terrific news because it looked like we were going to be a little bit on the low side, but April has been a surprise. And for water supply, things are looking better for most areas. Things are going to be a little on the low side for parts of the lower Snake River Valley and even parts of the Spokane River as well. And then we have to look toward drought conditions. We did have a little expansion of drought conditions over the last several weeks since things were kind of quiet across March. So we have some extreme drought in parts of central Washington, severe drought, a little bit bigger, but pretty much between the Cascades and the Panhandle Mountains, there's dryness that we're going to have to be monitoring. And it looks like as we go through the seasonal outlook, we're going to see these conditions persisting, especially as we go through the summer months, because we know we don't get too much in the way of precipitation, especially widespread precipitation as we go through the summer. And how does this play out for our significant wildland fire potential? So as we go through our summer months, that's when we get into fire season, and things, I know for June are pretty quiet in our area, but they're going to start clicking above normal, especially for the east slopes of the Cascades by July. And then into August, it kind of fills in across much of eastern Washington. So we're just going to have to wait to see what happens with that. So the outlook for April, that was just released just last week, continues the trend of below normal temperatures, which is going to keep that snowpack lingering on, especially if we keep precipitation above normal as well for May. So keep looking for a cool and unsettled May. And then as we go through May, June, July, it looks like things will be starting to warm up and dry out as we get into the summer season. So, yes, we've made it to the end. And I want to thank you for listening. And I know I've seen lots of questions that have trickled in, so I hope to be answering these very quickly. So what can you expect next? So I'm going to be going through and be emailing you within the next week and getting you those registered for being a weather spotter, all in our database, assigning spotter IDs and getting spotter training certificates out to you. So expect this coming in the next week. And just keep in mind, here's our office webpage that you can send us your reports, and know that your reports are very important. You help us get the message out to save lives. So I want to thank you for listening this evening.